Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Lagrangian of a charged particle from paper Electromagnetic Theory. So students, let us see what we are going to learn in this module. We are going to learn about the Lagrangian and Hamiltonian formalism in Newtonian mechanics, Lagrangian formulation for relativistic mechanics and Lagrangian of a non-relativistic particle, Lagrangian of a relativistic charged particle in the presence of electric and magnetic fields but in a non-covariant treatment, the Hamiltonian of a relativistic charged particle in the presence of electric and magnetic field but in a non-covariant treatment, the manifestly covariant treatment of the Lagrangian and the Hamiltonian formulation. Lagrangian and Hamiltonian in non-relativistic mechanics. Although the equations of motion are sufficient to describe the motion of a charged particle in external electromagnetic field, it is useful to consider the formulation of dynamics from the Lagrangian and Hamiltonian point of view. We begin with a very short review of the Lagrangian formulation of classical mechanics. In a certain sense, Lagrangian mechanics is only a free formulation of Newtonian mechanics from a practical point of view, whereas in Newtonian mechanics we deal with forces which are vector quantities. In Lagrangian or Hamiltonian formulation, we deal with a single scalar function of generalized coordinates and velocities or momenta. Newtonian mechanics works very nicely in Cartesian coordinates, but it is difficult to switch to a different coordinate system. Sometimes as simple as changing to polar coordinates is cumbersome. Finding the equations of motion of a particle acting under a central force as polar coordinates is tedious. The Lagrangian formulation, in contrast, is independent of the coordinates, and the equations of motion for a non-Cartesian coordinate system can typically be found immediately on using it. However, much more importantly, it puts the foundation of mechanics on very broad basis from which an extension to other physical systems become clear, or you can say it brings out the connection with other physical systems, quantum mechanics, statistical mechanics, electrodynamics, field theory and so on, and emphasizes the uniformity of the underlying principles and the basis of physical phenomena. The Lagrangian treatment is based on the principle of least action or Hamiltonian's principle. In non-relativistic mechanics, the system is described by a set of n generalized coordinates qi, t and velocities qi dot t, and being the number of degrees of freedom. The Lagrangian is a scalar functional in ordinary three-dimensional scale of qit and q dot I t and perhaps of time as well. The action A is defined as the time integral of the Lagrangian L along a possible path of a system. The principle of least action states that the motion of system is such that in going from a configuration A at time t1 to configuration B at time t2, the action will be A is equals to integral from t1 to t2 L dependent on qit, qi dot t and t dt, which is an extremum. By considering small variations of the coordinates and velocities away from the actual path and requiring del A equals to 0, the condition for the extremum, we obtain the Euler-Lagrange equation of motion. That is, d by dt of del L by del Qi dot minus del L by del Qi is equals to 0, where I is equals to 1, 2, 3 up to n. Given the Lagrangian L dependent on Qi dot and T of a system, we can define the Hamiltonian H. Whereas the Lagrangian is a function of generalized coordinates and generalized velocities, the Hamiltonian is to be regarded as a function of generalized coordinates and generalized momenta defined by Pi is equals to del L by del Qi dot, and the Hamiltonian is defined in terms of the Lagrangian as H dependent on Qi, Pi and T equals to summation of I from 1 to n up to Pi Qi dot minus L dependent on Qi dot and T. The generalized velocities, of course, have to be eliminated by the use of this equation, which is in principle can be solved for Qi in terms of Pi. The Hamiltonian equations of motion, which are completely equivalent to Euler-Lagrange equation, can be derived from them and are del H by del Qi equals to minus Pi dot and del H by del Pi equals to Qi dot. Let us apply these equations to some simple case of non-relativistic classical mechanics. If T is the kinetic energy of the particle and its Lagrange is given by L dependent on x, x dot and T is equals to capital T, which is equals to half mx dot square, which implies del L by del x dot is equals to mx dot, or del L by del x equals to 0, which implies mx double dot equals to 0. This is the equation of a free particle moving along the x direction. The generalized momentum is P equals to mx dot, the same as ordinary momentum, and the Hamiltonian is H equals to P square by 2m equals to capital T, that is the energy of the particle. If T is the kinetic energy and V the potential energy of a particle, and L dependent on x, x dot and T is equals to T minus Vx, which is equals to half of m x dot square minus Vx, which implies del L by del x dot is equals to mx dot. Del L by del x is equals to minus of del V by del x, which implies mx double dot is equals to minus del V by del x equals to fx. This is the equation of motion of a particle moving under the action of a force Fx represented by potential Vx. The generalized momentum is P is equals to mx dot, the same as ordinary momentum, and the Hamiltonian is H equals to P square by 2m plus Vx equals to T plus V, the total energy. Thus, if we believe that A is Lorentz invariant, then so is gamma L. The statement of invariance greatly limits possible form of the Lagrangian. Let us first consider the case of a free particle. Lagrangian for relativistic motion of a free particle. We wish to now extend this formalism to the relativistic particle of a charged particle moving under the action of external electromagnetic fields and consistent with the requirements of special theory of relativity. Let us first present the straightforward treatment of the problem, in which we continue with the ordinary coordinates and the velocities but generalize to the non-relativistic domain. At the end of this module, we will present the more sophisticated covariant treatment. Let us first consider the equation of the Lorentz transformation properties of the Lagrangian. From the first postulate of relativity, the action integral must be a Lorentz scalar because the equation of motion are determined by the extremum condition, that is del A equals to 0, and they must be the same in all frames of reference. Or we may think of invariance of A as an assumption or postulate in its own right and see where it leads to us. If we introduce particles proper time tau in equation through dt equals to gamma d tau, where gamma is 1 divided by under root of 1 minus u square by c square and u is the velocity of the particle, then the action integral becomes A is equals to integral from tau 1 to tau t of gamma L d tau. What invariance we may construct from properties of a free particle? We have only the momentum 4 vector p mu and the position 4 vector x mu. The presumed translation with invariance of space rules out the use of the latter. That leaves only the momentum 4 vector p mu and the single invariant p mu into p mu equals to n square c square, which is a constant. Hence, we are led to gamma L equals to c, a constant. To find the constant c, we appeal to the non-relativistic limit and expand in powers of u by c. Hence, L is equals to c by gamma, which is equals to c into under root of 1 minus u square by c square equals to c into 1 minus half u square by c square, and so on. On comparing with the Lagrangian half mu square for the non-relativistic case, we have c is equals to minus mc square. The first term of the series is constant, and arbitrary constant can always be added to Lagrangian without changing anything. And therefore, L free is equals to minus mc square into under root of 1 minus u square by c square. On applying the Euler-Lagrange to the above Lagrangian, we obtain the equation of motion of a particle, that is d by dt of m gamma u is equals to 0 or dp by dt is equals to 0. Lagrangian for a charged particle in electromagnetic field. Now we come to the problem of finding the Lagrangian for the motion of a charged particle in an external electromagnetic field. For a particle of mass m, charge q and velocity u moving in an external field E and B, the equation of motion is the Lorentz force equation, which is dp by dt is equals to q of E plus u cross b. We also have the energy change equation dw by dt equals to q u dot E. The magnetic force being perpendicular to the velocity does not do any work. We have used the symbol W for energy not to confuse it with the electric field. Now together these two equations can be put in a covariant form. That is du alpha by d tau is equals to q by m f alpha beta u beta. Here u alpha is equals to gamma c comma gamma u is the force velocity and f alpha beta is the field force tensor. The general requirement that gamma L be Lorentz invariant allow us to determine the Lagrangian for a relativistic charged particle in external electromagnetic field, provided we know something about the Lagrangian or the equations of motion of the non-relativistic motion of the particle. The total Lagrangian is L equals to L free plus L int, where L int is the interaction Lagrangian and contains the information about the fields and forces. For the interaction to be invariant, it must be case that A int should be equals to integral tau 1 to tau 2, whereas L int is the interaction Lagrangian and contains the information about fields and forces. For the interaction to be invariant, it must be case that A int should be equals to integral from t1 to t2 L int dt, which is an invariant, which implies that gamma L int is an invariant. Now, in the non-relativistic limit, we have L is equals to T minus V. A slowly moving charged particle is influenced prominently by the electric field, and the potential energy of the particle to the lowest order is V is equals to Q phi, where phi is the scalar potential. So, we have in this limit that gamma L int is equals to minus of gamma Q phi equals to minus Q phi W by mc square equals to minus Q by m P naught A naught. The Lorentz invariant expression for gamma L initial that reduces to this form in the non-relativistic limit is gamma L int is equals to minus Q by m P alpha A alpha equals to minus Q by m into gamma m phi minus gamma mu dot A. Thus, L int is equals to minus Q by gamma m into P alpha A alpha is equals to minus Q phi plus Q u dot A. This choice of interaction Lagrangian reduces to the correct static limit. It is the simplest choice for the interaction Lagrangian with the following properties. Possesses translational invariance, that is, it does not depend on x, the potential do depend on it. Is linear in charge momentum and fields, does not involve time derivatives of P alpha. Combining the two terms L free and L int, the total relativistic Lagrangian for a charged particle is L equals to L free plus L int equals to minus mc square into under root of 1 minus u square by c square minus q phi plus q u dot A. We can now find the equations of motion by using the Euler-Lagrange equation. On using the relation dAI dependent on xt and t divided by dt is equals to del AI by del t plus del AI by del xj into dxj by dt is equals to del AI by del t plus u dot del into AI. Putting all these into equation, we have d by dt of del L by del ui minus del L by del xi equals to q of del AI by del t plus u dot del AI plus dpi by dt plus q del phi by del xi minus q del by del xi of u dot A equals to 0, or dp by dt equals to minus q of del A by del t plus del phi plus q of del u dot A minus u dot del A. Thus, the finally expected dp by dt is equals to q of E plus u cross b where the first term is the electric field and the second term is U cross B. We next give a Hamiltonian description of the system. We first define the canonical momentum P conjugate to the position coordinate of the particle x by Pi equals to del L by del Ui equals to gamma MUI plus QAI, or P is equals to P plus Q dot A, where P is equals to gamma mu is the ordinary kinetic momentum of the particle. The Hamiltonian H is a function of coordinate x and its conjugate momentum P and is defined in terms of Lagrangian as H is equals to P dot U minus L. Since the Lagrangian is a function of x and u, but Hamiltonian is a function of x and p, therefore it can be expressed in terms of momenta rather than velocities. Thus, velocities has to be eliminated from the above equations. So, we'll get p square equals to p minus qa whole square is equals to m square u square divided by 1 minus u square by c square, which implies u square is equals to c square p square divided by p square plus m square c square, which implies gamma is equals to under root of p square plus m square c square divided by mc. This leads to u is equals to c P minus QA divided by under root of P minus QA whole square plus M square C square, so that H x P is equals to C under root of P minus QA plus M square C square plus Q phi. Now it is an expression for the total energy W of the particle. It differs from the free particle energy by the addition of potential energy Q phi and by the replacement P from P minus QA. Now bring the E phi terms to the LHS and we'll do the squaring. Then we'll get W minus Q phi whole square minus C square P minus QA whole square equals to m square c square whole square. This is just the 4 vector scalar product, that is p alpha into p alpha equals to m square c square, whereas p alpha is equals to E by c, or p equals to half W minus Q phi or P minus QA. So we see that the total energy W by C acts as the time component of a canonical conjugate for momentum P alpha, of which P given by the equation is the space part. A manifestly covariant approach leads naturally to these 4 momentum. What about the Gauss transformation properties of the Lagrangian? And the Lagrangian, being a function of potential phi a, is Gauss dependent. The equation of motion depends on the fields and are obviously gauge independent. However, the change in the Lagrangian on a gauge transformation is represented by addition of a term which is total time derivative of a function of xt, and in addition to a total time derivative does not alter the action integral or the equation of motion. To give a manifestly covariant description of the Lagrangian and the Hamiltonian formalism, the customary variables x and u must be replaced by their 4 vector counterparts x alpha equals to ct or x and u alpha is equals to gamma c or gamma u. The free particle Lagrangian can now be written in terms of u alpha as L free is equals to minus mc by gamma into under root of u alpha into u alpha. Then the action integral A equals to minus mc integral from tau 1 to tau 2 of under root of u alpha dot u alpha d tau. Of the 4 components of the 4 velocity, only 3 are really independent because of the constraint equation, that is u alpha into u alpha equals to c square, which implies u alpha into du alpha by d tau is equals to 0. This has to be incorporated into the equation of motion. We cannot freely vary this action to find the equation of motion. Now the integrand is under root of u alpha into u alpha d tau is equals to under root of g alpha beta u alpha u beta d tau equals to under root of g alpha beta dx alpha by d tau into dx beta by d into d tau is equals to under root of g alpha beta dx alpha dx beta. This is a very small length element in 4 space. This suggests that the action integral may be replaced by A is equals to minus mc integral from tau 1 to tau 2 under root of g alpha beta dx alpha by ds dx beta by ds into ds. X alpha s is the 4 vector coordinates of the particle, where s is a parameter that is monotonically increasing as a function of tau but otherwise is arbitrary. The action integral is an integral along the world line of the particle, and the principle of at least action is the statement that the actual path is the longest path and the geodesic. We now treat each dx alpha by ds as an independent generalized velocity, so the Lagrangian takes the functional form L dependent on x alpha dx alpha by ds and s. After the calculus of variation has been completed, so we identify under root of g alpha beta dx alpha by ds dx beta by ds into ds is equals to d tau, and we impose the constraint. A straightforward variational calculation yields the Euler-Lagrangian equation, that is mc into d by ds of dx alpha by ds divided by under root of dx beta by ds into dx beta by ds whole ds is equals to 0. Now imposing the constraint, we have m d square x alpha by d tau square is equals to 0 as expected for free particle motion. The Lagrangian for a charged particle in an external field suggests that the manifestly covariant form of the action integral is A equals to minus integral from tau 1 to tau 2 of mc under root of g alpha beta dx alpha by ds dx beta by ds plus q dx alpha by ds a alpha x ds. The Euler-Lagrangian equation now takes the form d by ds of dl by del dx alpha by ds minus del alpha L is equals to 0. The Lagrangian L is equals to minus of mc under root of g alpha beta dx alpha by ds dx beta by ds plus q dx alpha by ds a alpha x. Let us find the equation of motion of charged particle from this Lagrangian. The derivative of L with respect to dx alpha is del L by del dx alpha by ds is equals to minus del by del dx alpha by ds into mc under root of g beta gamma dx beta by ds into dx gamma by ds plus q dx gamma by ds a gamma x equals to minus half mc g beta gamma dx beta by ds dx gamma by ds raised to power minus half del of del dx by ds into g beta gamma dx beta by ds into dx gamma by ds minus q del by del of dx alpha by ds of dx gamma by dx a gamma x. We have changed the dummy indices in L from alpha beta to beta gamma since an index cannot be used more than twice. So therefore, we can rewrite the above equation as del by del of dx alpha by ds into g beta gamma dx beta by ds dx gamma by ds is equals to g beta gamma into dx gamma by ds into delta alpha beta plus dx beta by ds into delta alpha gamma is equals to g alpha gamma dx gamma by ds plus g beta alpha into dx beta by ds equals to 2 dx alpha by ds, or del by del of del x alpha by ds into dx gamma by ds into a gamma x equals to del of del dx alpha by ds into d gamma by ds into a gamma x equals to del of x. Del by del of dx alpha by ds of dx gamma by ds a gamma x equals to del by del of dx alpha by ds into dx gamma by ds into a gamma x equals to delta alpha gamma a gamma x equals to a alpha x. Hence, del L by del dx alpha by ds equals to minus mc into g beta gamma into dx beta by ds into dx gamma by dx raised to power minus half into dx alpha by ds minus q a alpha, and d by ds of del L by del dx alpha by ds is equals to d by ds of minus mc g beta gamma dx beta by ds dx gamma by dx raised to power minus half dx alpha by ds minus q a alpha x, and this is equals to minus mc d by ds of g beta gamma dx beta by ds dx gamma by ds raised to power minus half dx alpha by ds minus mc g beta gamma dx beta by ds dx gamma by dx raised to power minus half into d by ds of dx alpha by ds minus q of d by ds a alpha x, and minus mc d by ds into g beta gamma dx beta by ds dx gamma by ds raised to power minus half dx alpha by ds minus mc g beta gamma dx beta by ds dx gamma by ds raised to power minus half d square x alpha dx square minus q del a alpha by del x gamma into dx gamma by ds. The second term is del alpha L is equals to minus del alpha of mc into under root of g beta gamma dx beta by ds into dx gamma by ds plus q dx gamma by ds into a gamma x equals to minus q dx gamma by ds del alpha A gamma x. Now at the end of calculation, we apply the constraint g beta gamma dx beta by ds into dx gamma by ds whole under root is equals to c and replace s by tau. So as a result, we have d by ds of g beta gamma into dx beta by ds into dx gamma by ds raised to power minus half equals to 0, or g beta gamma into dx beta by ds dx gamma by ds whole raised to power minus half equals to 1 by c. So we have minus m d square x alpha by d tau square minus q by c del a alpha by del x gamma dx gamma by d tau plus q dx gamma by d tau into del alpha a gamma x equals to 0, or m d square x alpha by d tau square equals to gamma, or m d square x alpha by d tau square equals to q into del alpha a beta minus del beta a alpha into dx beta by d tau equals to q f alpha beta dx beta by d tau, which is the covariant form of the equation of motion. The Hamiltonian equations are dx alpha by d tau is equals to del h by del p alpha is equals to 1 divided by m into p alpha minus qa alpha, and dp alpha by d tau is equals to minus del h by del x alpha equals to q by mc into p beta minus qa beta into del alpha a beta. Now some problems with this Hamiltonian are: Hamiltonian is the time component of a 4 vector. The above Hamiltonian is a Lorentz scalar, not an energy-like quantity. Furthermore, because of u alpha into u alpha equals to c square and p alpha equals to mu alpha plus qa alpha, h is equals to 0. Clearly, such a Hamiltonian formulation differs considerably from the familiar non-relativistic version. So students, let us summarize what we have learnt in this module. This module is devoted to the Lagrangian and the Hamiltonian formalism for a charged particle in the presence of electromagnetic field. The idea of Lagrangian dynamic in non-relativistic classical mechanics is reviewed. The Lagrangian for the relativistic motion of a free charge particle is derived and then extended to a charged particle in the presence of electromagnetic field. Next, the relativistic charged particle in the presence of electromagnetic field is described in a Hamiltonian formulation and the Hamiltonian of the particle obtained. The treatment so far is relativistic but non-covariant. The theory is then reformulated in an explicitly covariant form. Thank you.